Welcome to this explainer. Today, we're diving right into some truly fascinating insights from Anna Gotowska and IBM Technology to answer one core question. How exactly does artificial intelligence decode the messy, interconnected fabric of our reality? We hear a ton about AI these days, but we actually rarely talk about the specific structures that allow these machines to comprehend the complex, web-like nature of the real world. Well, that is exactly what graph neural networks, or GNNs, are built to do.
So here's our roadmap for today. First, we'll look at our world of networks. Second, graph neural network basics. Third, decoding message passing. Fourth, modern GNN architectures. And finally, we'll wrap up with AI and complex graphs.
All right, let's kick things off with Section 1, our world of networks, the interconnected reality.
Think about it for a second. The real world doesn't run on neat, flat spreadsheets, right? It runs on networks. Whether you're looking at the topography of your own social circles, the precise 3D bonds of a chemical molecule, or just the vast, endless topology of the web itself, reality is a network. Now, traditional algorithms really struggle with this kind of unstructured connectivity, but this is exactly where graph-native AI thrives. If you want to understand how a specific molecule might react to create a new medicine, or say how a piece of information goes completely viral across a social platform, you absolutely have to understand the relationships and the links just as much as the individual data points themselves.
That brings us to Section 2, Graph Neural Network Basics, Foundation of Graph AI. So what is a GNN? Basically, graph neural networks are specialized machine learning models built natively for this exact type of web-like data. Instead of forcing these complex structures into rigid, traditional inputs, GNNs just embrace the chaos. They analyze an entity by drawing context from its entire connected neighborhood. They're not just looking at a single user or a single atom in total isolation. No, they analyze that entity based on everything it is actively connected to. This captures the deep structural context that standard neural networks literally completely miss.
But you might be wondering, how does a computer actually read a complex web of connections? Well, the secret sauce here is a concept called embeddings. This is how the AI translates these intricate, messy network shapes into a format it can actually compute. Think of an embedding as a highly compressed, mathematical summary of a network's characteristics. So, for example, by condensing a user's purchase history and all their friendships into a really dense vector of numbers, the AI can finally do the math required to give you highly accurate product recommendations. It's essentially this brilliant bridge between messy, real-world relationships and the very precise, mathematical world of machine learning.
Moving right along to Section 3, decoding message passing, the core mechanism.
If GNNs have a heartbeat, it is absolutely message passing. Imagine you're at a super crowded party. You connect with the people right next to you. You share some information directly. And then, based on what they just told you, you update your own understanding of the room. In a GNN, this translates directly to nodes in a graph. A node connects to its neighbors, it shares its current state, and then it updates its understanding based on the incoming data. After just a few rounds of doing this, every single point in the network holds a little piece of the global puzzle. It is just an incredibly elegant way for AI to learn the structural context of the data.
So, knowing what GNNs are and grasping this core mechanism of message passing naturally leads us to ask the big question: how do the actual modern AI models apply these concepts to understand complex graph data in the real world today? Like, what does the actual toolkit look like?
Let's open it up. Section 4, Modern GNN Architectures, the AI Toolkit.
Okay, here is the modern AI toolkit. First, we have graph convolutional networks, or GCNs. These kind of borrow from image processing to filter graph data, effectively smoothing out the noise in a network to find the core patterns. Then there are GATs, Graph Attention Networks. These introduce weighted learning, which basically means they teach the AI to value a close friend's data way more than a distant acquaintance, dynamically shifting its focus to the most relevant connections. Pretty smart, right? Then we have GraphSAGE. This was a massive breakthrough for scalability. Instead of needing the entire graph loaded at once, it generates embeddings for vast, unseen networks on the fly by just sampling local neighborhoods. Next up are GINs, Graph Isomorphism Networks. These provide the intense mathematical precision needed to distinguish between subtly different graph shapes, which is absolutely vital for comparing complex molecular structures. And finally, Graph Transformers. These actually adapt the powerful architecture behind those massive large language models to understand complex graph topology. They treat nodes almost like words in a sentence, but with multi-dimensional context. It's a whole ecosystem of models, each refining how machines interpret our interconnected world.
Finally, let's tie it all together in Section 5, AI and complex graphs, the big picture. Ultimately, the takeaway here is really profound. Through mechanisms like message passing and by deploying these highly specialized models, from GCNs to graph transformers, modern machine learning finally has the capability to truly understand the complex graph data that makes up our reality. By escaping the flat spreadsheet, we are fundamentally accelerating real-world applications. We're talking about speeding up drug discovery by accurately predicting how molecules interact. We're talking about catching financial fraud by analyzing entire syndicates rather than just looking at isolated transactions. And we're building hyper-accurate recommendation algorithms. AI finally sees the world the way it actually exists.
Which leaves us with one final and honestly pretty provocative question to ponder. As these models master the hidden networks of our lives, from our biology to our digital footprint, are we really ready for AI that understands the intricate web of our world even better than we do? Thanks so much for joining me today, and I'll see you in the next explainer.